banter going on. It's great. And I feel guilty stopping you guys from talking and socializing. Some days it's like I can hear crickets in here. So we left last time on Bernoulli's Principle. Showed you this. And this column went up higher, like this. Anybody take time to contemplate that and want to pose a solution? Yes? You're right. Did you read? What he said was, this part's narrower, which is what I was hinting at last time. It had something to do with that. Where it narrows, the air inside there actually goes faster. There's where a fluid, such as air, moves more quickly, there's an associated drop in pressure there. That's essentially what Bernoulli's Principle says when we try to apply that equation I wrote down last time. If the pressure here drops, then the pressure pushing on the top of that fluid is less, and it comes up. Remember, atmospheric pressure is still getting in here. And so it can get in there and there and there. And if it's pushing in, say over here, that pressure can be, if it's greater than this pressure, it's that difference in pressure, that gauge pressure, that would push it up. So again, the air moves faster here, so there's a corresponding drop in pressure, and so this part comes up higher. Can you see that these come up a little higher also? That's because the air is moving in there now. It is moving. It's just, it's not going as fast here as it is here. And that's because this is narrower. Let's make some sense of that with that equation. Last time I told you Bernoulli's Principle is essentially conservation of energy. And I wrote down 1/2 times the density times the velocity squared. This one's velocity. Density times gravity times height, plus the pressure, and that had to stay constant. Just rearrange it. You can think of, before pressure was what? Density times gravity times height. We did that before. It's force over area. That's what this works out to be in terms of density. Pressure is depth dependent. Well, look, here's the P term. It's like you could move it to one side. There's the potential energy term. It's just potential energy per volume. But now we have this term. This can cause a change in pressure. See, anymore I like to think of it like that. Shows us how this pressure changes. And it's really just how the energy changes. So if you have a column of fluid above you, that creates a pressure. And if you change your position, you change the pressure. Well, if the fluid is moving now, that can create a change in pressure. And as you see, the faster it goes, there's actually a drop in pressure. Let's look at that. Up here, yeah, because I guess technically, this would be a minus sign, wouldn't it? Show a decrease if you move that over. If this increases, then the kinetic energy term has increased. It's got more kinetic energy. But this has to stay constant, so what happens to the pressure? If this term goes up, this has to go down. That's Bernoulli's principle. Where the speed of a fluid increases, the internal pressure decreases. Yes?
Is that what causes lift on an airplane?
Yes, Bernoulli's principle can completely explain lift on an airplane. Interestingly, so can Newton's third law. They both can explain it. There's arguments out there like, no, you can only use this. No, you can only use this. If you're doing it all correctly, both can completely explain it. When things get funky and complex with certain airflows or whatnot, I would resort to Bernoulli's principle. But let's look at this. Let's look at an airplane wing since you brought that up. We'll do it now. So you got your wing. You're flying through the air. And what's it do? There's something called an angle of attack, and they tip it a little bit. And so the air rushes in here, and where does it go? It hits the bottom and gets deflected down. The airplane exerts a force on the air down. So what does the air do back on the wing? Pushes up. So in that sense, Newton's third law, action-reaction, that provides lift, an upward component. What's interesting is you can't just look at the air at the bottom. You have to look at the air at the top. The air that goes across the top, actually, due to something called the Coanda effect, stays kind of stuck to the surface. It follows the contour of it. And so it comes across and ends up being deflected down also. Well, that requires a force. If you're going to change its acceleration, or you're going to make it accelerate by changing its velocity, in this case, just the direction even changes the velocity, there must have been a force. So again, the wing or the airplane exerted a force on the air down, so the air pushes back up on the airplane, and both the air on the bottom and the top are providing a lift force. Now let's look at Bernoulli's principle. The air going across here, you know what, I'm going to come back to that one, because it'll be easier after I finish this. I'll come back to that. So another way to think of Bernoulli's principle is fluids in motion exert less pressure on their surroundings the faster they move. Again, that's just this. You go faster, the pressure drops. Don't think of it, though, as a cause and effect. If the pressure drops, then the fluid speeds up. They go hand in hand. Let's go back to this then. Why does it speed up when it goes through the small? Has anybody asked that in your head yet? Okay, good. You see, I just gave it to you. I just told you, but why? That's another concept the book talks about called the continuity equation. Continuity. So let's understand that before we move further. Basically, it says the amount of fluid, the rate at which it flows through your container, this pipe in this case, stays the same. In other words, I blow air into it, well, the same amount of air comes out. If you constrict it, can as much air get through here, volume-wise? No. So how does it keep up? We don't get a backlog of air. It goes faster, because less can get through there, so it goes faster to keep the same flow rate. Does that make sense? You can think of it as water, because that's a fluid, that would work. Your garden hose. There you go. You're spraying your water out the end of your garden hose. You put your thumb over the end, and you narrow the opening. What's the water do? It comes out faster. Same idea. That's the continuity equation. So if you have a pipe like we do, and it gets smaller. So over here, say you have area 2, and over here you have area 1, the cross-sectional area. Then where does it move faster? over here. V2 is greater than V1. It moves faster. The product stays the same. A1 times V1 is A2 V2. In other words, AV, that's all staying constant. And what's constant? The flow rate. So hopefully it makes sense. You constrict it down, less can get through, so it's got to speed up. So keep the flow rate the same. Right this way, you got big area over here in 1, so little velocity equals small area over there, bigger velocity. The product stays the same. We like playing, well, I like playing this game. It's easier for me to conceptualize it. So that's why the smaller area goes faster. Then, according to Bernoulli's principle and conserving energy, the pressure will drop at that spot. Let's look at the actual fluid. They're called streamlines. Fluid here will just kind of go straight through. They call these streamlines. If you have one up here, it like gets to here and it's forced down in there. Same with one over here. One up here. You get the idea. Those are the individual streamlines. They're constricted. You can see there's a force on them to push them in down in there. Anytime that your container changes the direction of those streamlines, there's an associated force, and the velocity changes. So now I can go back to my airplane wing here. The air on the top, it's like the fluid's coming nicely, and then it sees this bump on the top. And so it's like it gets constricted. It's like it gets narrowed at that spot. So what happens to the air on above the wing? It goes faster, just like this. See if I can draw that one today. So let's see, you got an airplane wing, typically it kind of looks like that. So you got some streamlines coming in. Here comes the air. And it gets constricted and follows it due to the Coanda effect and comes off. This one comes in, constricted, narrowed. A little bit. As you get further away, these are less affected. If you're way up here, you might not get affected at all. At the bottom, that didn't hit anything. But it runs into these. Until you get too far away, there's not much of an effect down here. So it should look something like that. There's better pictures online. But can you see it's effectively constricting the spot there. You can visualize it with the streamlines. And so Bernoulli's principle tells us the area got smaller, or the continuity equation tells us the area got smaller, so the velocity goes faster. There's thus a corresponding drop in pressure up there. The pressure here at the top is less than the pressure down here at the bottom. So what happens? It goes faster at the top. And what happens to the wing itself? See the difference in pressure? This is smaller, this is bigger. It gets pushed up. That difference in pressure acts over the area of the wing, the airfoil, and exerts an upward lifting force, which will be exactly equal to the reaction force from Newton's third law. From directing, see how the air is going down now? From going over the top and the bottom? Actually, most of the air is directed down because of the air that went on the top, more than the bottom. See, this actually has no angle of attack. But the top is still deflected down because of that contour. Airplane wings can even fly upside down if they adjust their angle of attack. Boomerangs, one of my favorite toys. They're an airfoil. They're curved. So when they cut through the air goes across them. And the side that constricts the air more, increase in speed, thus less pressure on this side than this side. So what will happen? It'll go like that. It's getting pushed. Something else we haven't studied is if things are spinning, they have angular momentum. And so actually what that means when it gets pushed here, because it's spinning, it effectively makes it rotate that way. And this thing will start curving, just like you'd expect. But that lifting force is because of the difference in pressure. Higher pressure, lower pressure. Because the air is moving faster on this side than it is this side. It gets pushed and rotates. Comes back to you. I love boomerangs. You go, Tina. Okay. You didn't flinch. Good. All right. Piece of paper. So some applications of this. You guys see it in lots of places. Monday, see, I was going to mention it, but I didn't get to this part. Who had your umbrella out Monday? It was pretty windy. Look at the air blowing across the top of your umbrella. Your umbrella's curved, right? So where's the air going to go faster? On the top. So where's the pressure less?
Pressure less.
Less. Yeah. On the top. So when the air blows across your umbrella, there's a drop in pressure here. The greater pressure lifts your umbrella. Has it ever tried to fly away from you? Playing Mary Poppins? That's why. You can just blow across a piece of paper. I'm going to force the air to go faster over the top. And you can see it lift. Some other ways to do it. Call this my smoker's test. This is open to the air. This is open to the air. A light styrofoam plug can slide. If you can blow it fast enough across the top, then the tube will constrict the air there, like the top of the airplane wing. The air is going faster there. A drop in pressure. And the atmospheric pressure down here should push this up. Anybody want to try? Want to try, Tina? Since you're right here. Blow across the top. Let's see if we can get it to come up.
Not blowing hard enough.
Faster. If we can make it go fast enough, there's a greater pressure.
I'm not fast enough.
I'll give her a clue. It's not just how fast you do it, it's the angle you blow. You don't want to blow into the tube. That'll just add air in there and increase the pressure. Angle up a little like this. Angle it this way so that it gets constricted. Instead of blowing in, aim that way. Put your lips down here.
Like this?
Lower. Yeah, yep. Oh! It went up until it yeah, you did it. I don't want you to pass out. But thanks for helping. So yeah, if you blow into it, that just smushes the air. And actually aim up a little, like right about here. And it's a piece of cake. You purse your lips too, that can help it go faster instead of just halitosis doesn't do it. So you can try this at home. You take a ping pong ball, it can slide through here. Cover the bottom, but the air needs to get there, so I actually open my fingers so that the air can get through. Blow across the top. See if you can get the ping pong ball to come up. It's lifted up. Now, I'm making that look easy. It might take you a few tries. Go home, perfect that, and then move on to a toilet paper tube. It's a little harder. So close. There we go. All right, if you can get those to move, then you can try. Let's do it without a tube. This acts like a wing on both sides. It's like you have the ball. Whew, a little woozy. Okay. Air comes up. And it gets deflected. Follows the contour. A little bit, a little bit. So here it's constricted, here it's constricted. Pressure, lower. Pressure, lower. Because it's going faster, right? V, faster. V, faster. And the pressure here is higher. Pressure here is higher. So it actually stays in the airstream. Because every time it wants to move out, the higher pressure pushes it back in. It's higher out here too. This is atmospheric pressure. Difference pushes the ball back. And same on this side. So if you can get air going around the ball fast enough, you can hold it up. What do you think? Yeah, I can't do it. But this can. Do you see how you could even tip it? So the air's like this. That means the air on here is being deflected even more than the air down here. It's the airplane wing. And you're getting upwards lift, even when it's off to the side in the airstream. The pressure here is less than there. And so that provides enough to counter its weight. Remember, because the net force would be zero. The weight down, the lift force up, are balanced if it's staying put. Yeah? I was just thinking, aim it at the ball, point straight at the ball. And like the ping pong ball, it naturally goes around because it's deflected. It gets constricted, speeds up because of the continuity equation, and then Bernoullis Principle conserves energy, takes over, and the pressures adjust and hold the ball up.
So why can't it work on an angle better with the beach ball than the red ball?
This is heavier, actually, than this. So this requires more lift force. A greater difference in pressures.
If like an airplane had a bigger curve, would that create less pressure or more pressure?
What do you think? So if this had a bigger curve,
Yeah.
well, it would get constricted more.
Right.
Thus, greater velocity, less pressure. To a point. I mean, you get a big old clunky...
Yeah.
It still needs to be aerodynamic so that it can come off. You don't want it to come off of the surface. You want to stay following the contour. Otherwise, its release creates turbulence, and that adjusts things and messes things up. You can also have too great of an angle of attack. Be like this. Good, good, good. But at some point, again, see, it comes off over the top. You lose all this effect. The airplane stalls, and you nosedive. Ah. Let's do it this way. What do you think will happen now when I turn on the fan? Will it hold it up? It's blowing air up? How come? Yeah, it spreads out. And what's it do when it spreads out? Slows down and increases the pressure. It goes the other way. It actually doesn't hold it up at all. But here's my favorite part. It actually, because as the air spreads out, the pressure becomes high again. But right there where it's narrow, the air is going faster. It's still constricted, so the pressure's less. Higher pressure, lower pressure, and it actually keeps the ball in the funnel, even when it's upside down. Did you follow that? This part's constricted, this part's not. There's the change in area, thus a corresponding change in velocity and a corresponding difference in pressure. This is the low pressure. This is the high pressure, and it holds the ball in. So in your homework and thing, you have lots of applications of this. Look for those things. Look for how the areas change, whether the airflow is getting constricted or not. Use the continuity equation to help you then process, okay, then that means the velocity is speeding up or slowing down. And then according to Bernoulli's principle, it means either the pressure is dropping or not. And it's those differences in pressure, those gauge pressures, that can exert forces when they're acting over areas, back to Pascal's principle. So I'm trying. You got enough tools now to answer all those questions. Do you have any right now? What if it, oh, yes.
So for this principle to apply, does it also need to be open to atmospheric pressure?
This works for any fluids. Any fluid. So even in your body, blood's flowing. Let's say you got blood in one vessel coming along like this, and then there's fluid in this one. The same thing would happen. There'd be a corresponding drop in pressure, and so it would lift the stuff in you, it'd lift the blood up. Old carburetors worked that way. With the air would shoot across here, and it would pull in the needed fuel, gasoline, into the air mixture and go in and get ignited. Atomizers, like with perfume and thing, where you squirt them out. What they do is they squirt air across the top of a tube that's in your fluid. It sucks up the fluid, pushes up the fluid, sprays it out. You guys have a question? Oh, okay. Alrighty then. Then, I got a few clicker questions for you, and then we can start the electrostatic stuff. While you're getting that out and logging in, I just learned yesterday, you might already know, but I'm warning you, because you have a class on this part of campus. ESPN College Game Day is coming to the U. They're starting to set up now, through this weekend. Woo. But they're going to pretty much take over President's Circle, which is why you can't drive in there right now. But realize traffic might increase quite a bit through the weekend. So if you got classes over here, so you're not late, you might have a lot of people in your way. So take that into consideration.
Because it's on Saturday, right?
Yes.
They're going to be there on Friday too?
They're starting to set up now. Yeah, from now until through the weekend. So be aware. Yeah, you have an excuse. Well, I'll know why you're late. That's true. Well, here's the first one. If you go higher up in the atmosphere, what's changing? How's everybody doing logging in? Okay, good, good. 45 of you, that's most of you then, normally. So, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Hey, that's the most we've ever had. 67 responses. Well, good. That means most of you are here. So that reminds me. Several days ago, I sent out another email about unassigned clicker device ID numbers. There are still several of you that are occasionally coming and responding because I'm getting responses from those unassigned device ID numbers, but I don't know who you are. So you either need to fix that or contact me or you're not going to get credit. All right. Oh, look, I stalled after it and we got some more people. All right. So the majority C, most of you, next A. You're absolutely right. Atmospheric pressure drops because you're not as deep in the atmosphere. Absolutely. You also, though, have a lot less air up there. So it's both of them. If you have less air up there, then it's less dense. Less mass for the same volume. So they both are actually changing. Questions? All right, consider two tubes then, one filled with air and one filled with water. When will the weights of those two fluids, the air and the water, be the same? What will the height of that water column be? Your clue is the one with air, it's atmospheric pressure at the bottom. The one with water, it's the pressure due to the column of water. So how much water do you need to balance atmospheric pressure? By the way, I didn't mention it, but those of you that are reading your book and get more information, the atmosphere is on average about 30 kilometers tall, so you'd be including all the air in the atmosphere. Ten, 9, get your votes in, 8, 7, 6, 5, 4, 3, 2, 1. Why are so many of you waiting? 0. Okay. 2/3 of you think it's 10 meters high. You're right. Pressure is density times gravity times height. If you plug in gravity and the density of water, to create a pressure equal to atmospheric pressure, you need 10.3 meters of water. And I mentioned that several times last lecture. Yeah? It's 760 millimeters of mercury. So a lot shorter column because the mercury's more dense. You don't need as much of it to create the same effect. Yes? And it's absolutely a barometer. The height of your column of fluid tells you what the pressure is. Yes. You could use a water tube as a barometer. It's just kind of impractical being 10 meters tall. So back historically they used mercury. It was more practical. All right, I like this one. You got a still tank used for storing gas. If you pump enough helium into the tank, what can happen? A steel tank. Pump helium into it. What can happen? These are good. They stretch your brain a little, give you some practice applying these skills. It's a nice, rigid, thick, strong steel tank. You can think of, one of those helium tanks used to blow up balloons, or think of a big tanker on a car, Or it can even be really small, but yeah, it's strong. It's rigid. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. 10 seconds isn't enough to pick an answer? Or just because you don't know what the answer is? Uh-huh. Well, wherever you're lying, here we go again. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Meh. Well, so what I like is it's either just floats like a balloon. No, you guys said it will bear down less or do nothing. I guess you guys need to talk to each other more. Reopen it. Talk some more. See what your friends are thinking. Told you this one was fun. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So I'm always stifled why you're not revoting again, but that's okay. Oh, it shifted a little to D, none of them. Well, this says a helium balloon is able to float only because its volume increases, thus displacing its own weight of surrounding air. That's the buoyant force, Archimedes' principle. A steel container that's rigid doesn't change its volume, so the buoyant force never changes. It's still displacing the same amount of air, whether it has helium inside it or not. But what actually happens when you put more and more helium inside it? It actually will weigh more because you're increasing the density inside. You're cramming it in. You're actually adding mass to it. It'll actually get slightly heavier. But the key here is it doesn't change shape. So the buoyant force, which is volume dependent, doesn't change. Does that help? Cool. One more. So you got a hot air balloon just hovering in the atmosphere. Net weight, so you know there's two forces. It's weight and the buoyant force. Are those equal, or is one bigger or smaller than the other? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. That's right. If it's hovering, it's not going up nor down, so the net force must be 0. The two must be balanced. Thus, it must be displacing its weight of displaced air. That's the buoyant force. The buoyant force equals its weight. To do that, it has to displace the same amount of weight of air. Questions? All right. Well, there we go. We're moving past fluids. And I'll do a little introduction here with charges. Chapter 22 and 23 are next. We'll deal with charges flowing in chapter 23 with current. But let's understand what charges are and where they come from and the forces between them to see why they would want to move in the first place. Most of you probably already know how many kinds of charges are there. I heard 3. What are they? Positive, negative, and neutral. What's neutral mean? No charge. So we don't actually count that as a charge. So yeah, there's 2. Positive and negative. Do you know where they come from? What's the source of that charge? Protons and electrons. All material is made up of protons and electrons, atoms. Remember, the protons are in the nucleus? They're positively charged. The electrons are orbiting around. They're negatively charged. The neutrons are neutral. They're in the nucleus also. So if you remove a few electrons, get rid of some of the negative charge, then you leave the atom electrically charged. It has a net positive charge because you removed some of the negative charge. It's now an ion, if you remember your chemistry. If one gains extra electrons, it has a net negative charge, and we say it's charged negatively. So that's where they come from. You can transfer them by rubbing things together. It's not the friction, it's every time they separate, every time they come apart. Rubber has a greater affinity for electrons. If you remember your periodic table, on the right-hand side, they are almost full of their outer shell with electrons. If some of you remember that, their electronegativity. If they had a couple more electrons, they could be full and more stable. So they're more likely to grab electrons. And who do they grab them from? The left-hand side, that only has a couple. They'd be happy if they could just give those up. They could go back down to the next full electron level shell and be stable. So those materials are more likely to give them up. Well, hair tends to give them up, and rubber tends to grab them. And so this becomes negatively charged, the rubber rod. So I'll charge it up, put it on this pivot, do a second one. Every time this rubber separates from the hair, it becomes charged. These should both be negative. What do you think will happen? Right. Same charges repel. Negatives don't like other negatives. There's a force. All right, let's do positives. Silk and glass. Glass likes to give up electrons, so it becomes negative. What do you think it'll do when I bring it near the rubber rod? They're opposite charges, positive, negative. They attract. Opposites attract. So there you go. Same charges repel, Opposite charges attract. There's positive and negative charges. Yeah. It'll stay there indefinitely if it doesn't have a path to escape. So that charge, though, will leave eventually through the moisture in the air. Water is conductive, allows electrons to flow across it. And so eventually they will escape through when they come in contact with the moisture in the air.
What about the ones how they get their electrons back?
Say that again?
What about the ones that want to give away their electrons? They can get them back the same way?
Yes. Yeah, you need some conductor to allow them to transfer back, either away or back, the deficit or the excess. Here is a tool called an electroscope. If I transfer these by physical contact, touch different surfaces, then those charges transfer onto this electroscope. They spread out because it's a conductor. They don't like each other. They repel. They go on that needle and they're pushed away. Can you guys see that okay? So that tells me that it's charged. I'm touching ground, so I'm going to allow a path so it can become neutral again. And now it's back into being balanced. There's an even amount of positive and negative charges. This method is called charging by conduction. Conduction. Physical contact, where you touch it, that is now charged negatively. It has more negative charges on it than positive. You can also charge something, though, by induction. Induction. You don't actually make physical contact. Watch what happens. I'm not going to touch the electroscope with the rod. Do you see it deflecting, though? It's being repelled. Why? That has charges in it. What do you think these negative charges do to those negative charges? Yeah, they push them away. What's it do to the positive charges in there? It attracts them. So internally they shift a little bit. And that's called polarizing something. This is now polarized. Polarization. We've induced a charge on it by induction. See, when I remove the rod, no charge remains. But now watch this. Watch closely. I bring it near. It's polarized. I'm going to touch it. I'm going to give those electrons that are getting pushed away a path to ground so they can escape. You ready? Doink. Now I'm going to let go. I never touched it with the rod, but it's now charged. Positively or negatively? It's positive. I removed the excess electrons, some of them, with my finger, which left, what's left is more positives. So charging by induction charges it up oppositely than conduction, where I did physical contact. If this is negative and you touch it, then those negatives can transfer to it, and that's negative. But if you don't touch it and then kind of ground it, you can charge it up oppositely. We'll discuss that more with some applications next time after this question.
So with lightning, with the ground then stay positive, even though it puts out the positive?
Yeah, there's a charge in your clouds, and when it moves above the ground, what's it do to the charges in the ground? Same thing. It polarizes it. Attracts one charge and repels the others. Yes. See you Friday.